perfect, right? So well, let's take a looky. All right. So let's take a look at 4.36F. I'll just throw it out there to my students who are all very astute. Did anybody find the longest chain in this one? How many carbons are in it? Just straight out of the textbook. Yeah, thanks, Sean. There's 10 carbons, right? So if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that would be the longest chain that has the most branches. Give me a thumbs up if you found that chain. Did anybody else find that chain? All right, sweet. That's great. Yeah. No, hold on. No, that isn't the right chain, is it? I made a mistake. I just realized that. Looking at it, could go like this. That would be. So let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. What was wrong with the first branch that I chose? It didn't have enough. It didn't have enough branching on it, right? This one's the longest chain with the most branching. Okay, so that was my mistake. So here I have an isopropyl group. Here I've got a methyl group. And then over here I have an ethyl group. Oh, there's another methyl group that I missed, this one here. I really don't want that longest chain. All right, so if I highlighted this carbon in green and highlighted this one in red, where should I start numbering from? It's not a trick question. Yeah, from the green one, absolutely. So I have, let's see here, let's put the numbers in it. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is some kind of decane. And I've got a 6 isopropyl, 2 4-dimethyl, and a 3 ethyl. So ethyl is going to come first. So I'll have 3 ethyl. Isopropyl should come next. So a 6 isopropyl. I'm going to run out of space here. So a 6 isopropyl. And then I have what? A 2 4-dimethyl. So we'll scribble that down. 2 4-dimethyl decane. There you go. All right. So 3 ethyl, 6 isopropyl, 2 4-dimethyl decane. Okay, let's try the next one, which is a bicyclo compound. This is a bicyclodecane because there's 10 carbons total in the bicyclic system. So we have bicyclodecane. Could anybody tell me what the 3 numbers are going to be in the brackets? Something, something, and something. Yeah, absolutely. Thanks. That's a 4, and a 0. Yep, absolutely. If I highlight this carbon in blue and highlight this bridgehead carbon in red, where should I start numbering from, the red or the blue? Yes, absolutely. All right, so I'm going to start numbering here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's see, I've got a 2, 3, 5, 9 tetramethyl. Oh boy, I'm going to run out of space for that, so I'll write it down here. 2, 3, 5, 9 tetramethyl bicyclo 440 decane. Anybody else get something like that? Cha? Good. All right. Let's try another one. K. So let me just draw K. I didn't draw it yet. So it looks something like this, where you have a bicyclic. It looks something like that. And then we have a methyl here and a methyl here. So this one, I think, I don't like to use the word easy in organic chemistry class because there's nothing easy in chemistry. But I think this one's easier than some of the other ones. Since it's completely symmetrical, it doesn't matter which bridgehead you start at. And every single bridge has 2 carbons, right? 2, 2, and 2. So this one's kind of fast. So let's just start with 1, and then we'll put 2, 3, 4, 5, 6, 7, 8. So we have a 1, 4-dimethyl. So we'll scribble that down, 1, 4-dimethyl. dimethyl bicyclo. 1, 2, 3, and our numbers are going to be, anybody? Two, two, two. Yep, I like the way you think. 2, 2, 2, and then we have a total of 8 carbons, so bicyclo 222 octane. And there you go. That's it. All right. Let's try one where you have to draw the bicyclo compound. So see if we can give this one a shot. So draw, and see if you can make out my handwriting. 2, 2, 4, 4, tetraethyl bicyclo 1, 1, 0 butane. So I want everybody to give a shot at this one. I'm just going to go get a drink of water. I'll be right back. All right, so if we want to draw this compound, we've got a bicyclobutane. So we're going to draw our 2 bridgehead carbons. Then we've got a bridge with 1 carbon, another bridge with 1 carbon, and then there's no bridge there's no third bridge. So then if we would number this, since it's symmetrical, you could go 1, 2, 3, 4, like that. So we have 2, 2, 4, 4 tetramethyl. So we're going to put an ethyl group here, an ethyl group here, here, and here. It looks like some kind of spaceship or something, maybe. All right. Here we go. Let's try another one. So I want to try one more problem, and then we'll call it a day. But I wanted to take a look at a problem where you compare 2 compounds again and see if you can figure out which one is more stable. So if we look at this compound, so if we have a methyl group going down, one coming up, and one going down, so I'll give you a second to draw that. And then if we have another compound where we have this methyl going down, this methyl going down, this methyl going down. I'm not doing very good at my dashes here with my apple. All right, this one going down, and this one coming up. Okay, so maybe I'll change the color. This one will do it in blue, and then this one will do it in red. Okay, so the question is, which one of these is going to be more stable? Would it be the blue one or the red one? Now you've got a couple of possibilities here. You can either just try the whole axial equatorial thing, or you could try drawing the chairs. Either way it's a reasonable idea. So the way that I solved the first one is I kind of did up and axial, down and axial, right? All that kind of stuff. So this time I thought it'd be more fun to try and draw the two chairs. So let's draw the two chairs in blue. And if you solved it the other way, there's nothing wrong with that whatsoever. Let's just try it because it's always a good time to practice drawing a chair, right? You can book a evening at a fancy restaurant. It's a good time, right? So let's see here. Let's number the carbons. I don't know. Let's do it like this. 1, 2, 3, and I'll pick 1, 2, 3. That would make this 1, 2, and 3 over here. Okay. So we'll start with the blue one. If the methyl group is pointing down, let's just do it as going down an axial just for the heck of it. So I'm talking about this methyl group right here. So it's going to be going down and oops, let me get my blue pen. It's going to be going down an axial. So that means that this methyl group, should it be pointing up an equatorial or up an axial? The one I have in the blue circle. And it's not a trick question. So if this one is down an axial, the next one is going to be up an axial. Right, down, if this is down an axial, right, axial alternates, up, down, up, down, up, down. So down an axial, that means that this is going to be up and axial, right? Right, there's no way anything here could be up and equatorial. It's impossible. Anything that's in an equatorial position has to be pointing down. So we'll delete that. So that means the methyl group at carbon 3, should it be axial or equatorial? The methyl group at carbon 3. Could anybody answer that? The methyl group at carbon 3, would it be down an axial or down an equatorial? It's pointing down. It has to be down an axial, right? That's the only possible way it could go, right? If this is down an axial, this is up an axial. This is down and axial, like that. So there we go. So now if we flip the ring, everything is axial in this one. So now it's going to be down and equatorial. This one's going to be up and equatorial. And this one is going to be going down and equatorial. So if I call this one A and I call this one B, which one is more stable? And it's not a trick. Yeah, definitely this guy, right? Okay. Everything is equatorial. All substituents equatorial. Okay, so now let's turn our attention to the one in red. So we'll do something very similar. In fact, you know what I'll do is I'll just copy those chairs and paste them. And then I'll delete little bits of it. So copy, see if I can do that. So come on, paste. Will this work? If I change the color to red, there we go. And then if I just delete this and this and this, there. Okay. So now we're going to do something very similar with the one in red. Okay, so we can squeeze them all on the screen. So let's just assume carbon 1, 2, and 3. If the group, this methyl group, if it's pointing down, we're going to assume it's down, or it has to be down. Son of a gun, where's my red pen? Down an axial. So that means the next methyl group, this one's going to be pointing down, and you go from down an axial, you go from down and to down and equatorial. Good. Yes, absolutely. So we have equatorial. And then the next methyl group is going to be going up. Would it be up an axial or up an equatorial? The next methyl group, the one I have circled in green. Up an equatorial, absolutely. Absolutely. So we have down and equatorial, then we have up and equatorial. Okay, so now if I flip the ring, so I'm going to give the ring a flip. One I'm going to hit. Okay. So if I flip the ring, now what was carbons 1, 2, and 3? This is going to be carbon 1, 2, and 3. So carbon 1 is going to have a methyl group, except it's going to be down and equatorial. The next one, carbon 2, the methyl group is going to be down axial. And in carbon 3, the methyl group's up, but now it's up and axial. So if I call this one, let me delete the A's and B's here. If I call this one A and I call this one B, which one's more stable? Which one's going to be more stable, A or B? Yes, absolutely. Right, there you go. That one's going to be more stable because you have 2 substituents, equatorial, 1 axial. All right. So if I compare the 2 compounds that are in the green boxes, if I call this one, I'll call this one C and I'll call this one D. Which one of these is more stable, C or D? There you go. It's going to be C because all substituents are equatorial. And so this one is going to be the more stable of the 2. That's kind of a long way of solving it, but it's a good way to do it. Somebody asked me, can you go over how you renumber from the bicyclo to the chair? So I'm not sure what you mean by the bicyclo, because a bicycle and a chair are 2 different things, right? A chair is when we take a cyclohexane and then we draw it in the chair form, right? So we can draw this chair, or we can flip the chair, draw it like this. So that's a chair. A bicyclo compound is something, you know, where you have 2 rings that are fused together, something like that. Does that make sense?
Yeah, it makes sense. I was just talking about the hexane in the chair, how you're numbering the carbons.
You can start anywhere you want, really, unless you're talking about nomenclature. You can start at any carbon you want.
Oh, okay.
So, yeah. So, I mean, if you pick this problem here, right, let me just select one thing. I'll just select this, right? So this is a drawing that I did of this compound. It doesn't matter where you start at all. There's no differentiation, right? Because you can move the ring. The ring is tumbling around in space. So let's imagine you drew your chair like this, okay? And you can choose this as carbon 1, this one, this one, this one. It doesn't matter. You can choose any carbon you want as carbon 1. It doesn't matter at all. If you pick this one, for example, 1, 2, 3, and you have to draw this compound. So let me just erase some of the spinach here. You just start drawing it, right? So on carbon 1, if you have a group pointing down, the down position is going to be an equatorial position. On carbon 2, you have something pointing up. It's going to be an equatorial position. And then on carbon 3, you have something pointing down. That's going to be an equatorial position. So these 2 compounds that I have drawn here, they're the same thing. I just flipped the ring. They're just different conformations. That's all. So the reason why I always do it kind of the same way, which is kind of the David Klein way of doing things, if you look at the solutions manual, right, since there are so many ways to draw a chair, this is not some kind of rule at all. But a lot of times in the solutions manual, he'll start with carbon number 1 in the top right corner. That's not a rule. That's not associated with any kind of IUPAC rule or organic chemistry rule. It's just the way he does it to simplify it. Because like I said, you could choose technically any carbon, but he tries to repeat himself a lot to make it easier. Does that make sense? Okay, yeah. There's, again, you can draw these chairs many, many different ways, right? A good organic chemist should be able to manipulate all of these different conformations in their mind and everything. All right. Well, let me just go back to my screen here.